Yes, yes, yes. So, Radek. Hallo, hallo Radek. Wie geht es? Hallo Radek, wie geht es? Hast du alle Geschenke gekauft für Christmas, für Weihnachten?
Ich verstehe nicht.
Okay, sorry, I thought you would be surprised. I'm trying my best in German, right? But you don't. You're always a step ahead.
Yeah, my only sentence I remember is ich verstehe nichts. So,
oh, schade, schade. I need to be smarter next time. I'll change to something new with the help of some AI technology, but it was just spontaneous.
We don't need to know anything, because AI will do everything. So
stupid attempt to make you to feel awkward. No. Sorry. So let's make it happen. The webinar is here. The webinar is here, and we are here too. And we will start in a couple of minutes. Radek, yes. And we should definitely make sure that everything works. So I guess you can see this will be the presentation. I will full screen it, and I hope. No, it's the last page, but this is the first page. So here we will start the presentation. I hope you can see it as usual. And what else we have? We will wait for the attendees and attendants and for people to come. And this works. So yeah, we'll make our standard webinar. We will talk about pretty much everything we find important, right? In the CFD simulations of these pumps. Yep, and that's pretty much it. Yeah. So shall we? What do? We have still 1 minute. We should finish our last talk, Radek, because I have been thinking about it very much. We started the talk about the flat Earth. Right, flat Earth, because some people believe that the Earth is flat, completely flat, right? It's not like a sphere, right?
Yes.
Radek, do you believe? Do you think that people who think the flat is Earth, the Earth is flat, do you think they also believe that the Moon is flat too? Right? This is what we discussed last time.
Okay, very interesting question.
Yes.
Maybe if there is any moon, then it should be probably flat. Yeah.
You can look. It's on the sky. It's in the sky. So
maybe just kind of reflection. It's just a reflection of something.
Yeah. so maybe, but I'm serious. Of course, we should ask them, right? But what do they think? Do they think it's what?
And what about the Foucault? How to say pendulum, right?
Yes.
How it works on a flat surface? I don't know.
Right. This thing. Yes. And a proof of what we think is the Earth is a sphere, right? A rounded object. Yeah. Those are the questions, and also the weather. And I guess we will start the webinar.
Yeah,
let's start
the webinar. Okay. The more interesting.
Yeah. Let's make it happen. I still. Oh well. I'm seeing that there are definitely Christmas out there because there are not many people here. And I guess no one else is coming, so we will start the webinar anyway. So I'll wait 10 seconds, then we will start.
So let's freeze for 10 seconds, yeah.
Hello, everyone. Oh shit! Oh, sorry. No. I was too optimistic. Sorry. Let's start it again. Another 10 seconds, because then I can see the the frequencies. Then I do the cut in on YouTube channel.
Okay.
It's easier to cut it if we wait another 10 seconds. Hello, everyone. This is from CFD support, and I would like to welcome you to the last webinar of this year, 2024. We are looking for the end of the year, of course. We are looking forward to Christmas and everything. And before we will go for our well-deserved holiday, we will tell you about what we think we should do about blood pump simulations and simulations of I would say small pumps and and simulation of pumps in general. Okay, so we will do the webinar is being recorded, and its recording will be later made publicly available on our YouTube channel, so you can see the recording. And also there will be a general part in the beginning. There will be a more practical part where Radek will show the more technical stuff about practical simulations. And in the last part, we will happily answer your questions if you have some. So feel free to ask your questions anytime during the webinar, and we'll be happy to answer them. Okay, so that's I guess it's the organizational information. I guess it's over. Feel free to ask questions anytime. That's the rule number one, and we'll do our best. Yeah. So I guess maybe we can switch the cameras off for a while to give users more comfort of better aspect ratio of the screen.
Yeah.
So I'm going away for a little while. Maybe we will come back later in the Q&A. Let's see if we make it. And I will slowly start. So first of all, today's webinar is dedicated to blood pumps or centrifugal pumps in general. There are also axial pumps, but I guess I know it's the topic for the future, because we are already working on very interesting project on axial pumps. But here we have the centrifugal pump. It's called FDA pump because FDA is a barrel in US, and they also have this, I would say, certified machine which transports blood. So it's also a benchmark because the measurement data is available, and the comparison of the simulation and measurement is available. So those are, pretty interesting cases when the measurement data are available. So it's interesting in this point. The pump itself, it transports blood. Maybe I should mention a little bit here that the rheological properties of blood are very interesting and specific, because blood is shear thinning fluid. That means the viscosity decreases with strain rate, with velocity gradient, I would say, or norm of velocity gradient. So the viscosity changes. Also, it's a viscoelastic fluid. It means it's not it has some elasticity, and it could be involved if we would go after this phenomena. And there are also really a lot of chemical reactions going on all the time in the blood, which is another important point. And maybe lastly, the phenomena which is called hemolysis, which is the red blood cells damage is happening where the strain rate is above a certain level, and that's another important point regarding the rheological properties of the blood. So all these I would say properties are important. In our today's webinar, we are not going directly for them. There's certainly all of them are possible to simulate, and all of them are possible to model. But in this webinar, we will rather strictly focus on the turbomachinery aspect and flow pump flow aspect, and we will deal with I would say kind of perfect fluid, which is water. So we will talk about water, but all these phenomena is it's definitely possible to use, and it's not very it's not very complicated, I would say, but okay, let's talk about it a little bit later. Okay, so I will say just a general information about our company. So the company is called CFD Support. We are located in Prague, Czech Republic. We are 15 years in the market, and we deal with CFD, primarily with CFD, computational fluid dynamics, and then we also deal with structural analysis, FEA and FSI. We deal with simulation-driven optimization and also with flow acoustics. Those are our main fields. We do consultancy projects, but our main product, our main product is simulation software, which is called TCAE. It's a comprehensive simulation environment, which allows its users to really do effective fluid dynamics simulations. So that's what we do. So I will talk a little bit about TCAE. So TCAE is a software which consists of modules. There are modules for meshing, modules for CFD, for FEA, for acoustics, for optimization, for example. TCAE is extremely flexible. It's ready to be used together with in-house codes, with open source codes, with commercial codes. It's really created from the beginning in a way to fit existing engineering workflows or create completely new workflows depending on the user's preference, skills, knowledge, resources, etc., etc. The beauty of TCAE is it's unlimited. That means there are no limitations on number of its users, jobs, cores, hardware installations, and you can be sure that you can use your resources to the fullest. There is a wide range of collaboration options. TCAE is based on open source. There are more than 60 open source projects in TCAE which work. They work together. We made it so. And also TCAE is focused on specific cases, and it allows TCAE to be accurate and really well automated and usable for the industrial cases. The way of it's being used is again very wide. There's a wide range of possibilities. So it can be used remotely, it can be used locally, of course, it can be used in a client server mode, or it can be of course it can be run on laptops, desktops, PCs, clusters, clouds, remotely from home, in work, or in Windows, in Linux. It can be used with graphical interface or in the batch mode. So there are really a lot of using options. And finally, there are a lot of resources. There are more than 50 tutorials which are based on real industrial projects we did in the past. We only changed a few details not to be recognizable, but there are more than 50 working proven tutorials. There are about 15 benchmarks which can be published publicly and discussed publicly and rerun and again. So it's very transparent. And also we have good technical support. We help our users, and it's our proud that we walk the journey of engineering simulations together with our users, and we are very proud of it. The new release is out like 1 or 2 months. It's 24.10. Again, we have released a new version with a lot of new features and improvements. And for the future, we will definitely focus on optimization workflows, because we believe it's really necessary and it's another level of doing simulations. We will focus on acoustics software and acoustic module, which we believe is really sophisticated, and not everyone can do that. And the new module will be created, and it will allow users to create their own surrogate models, which we believe again it's another great trend which is going on, and we are working on it currently. And also we decided after many years of having industrial clients, we decided to make TCAE accessible to everyone. So we released TCAE Lite, which is a special version of TCAE, which only includes T-Mesh and TCFD modules. So it's only CFD. The technical support is via forum, but anything can be run in TCAE Lite, and it's standalone software, and in the future we will develop it as a graphical interface for OpenFOAM, and it's as cheap as a daily cup of coffee. So it's really accessible to anyone. We believe it's accessible to anyone. Okay, so the benchmark, the FDA blood pump benchmark is today's topic. I would like to ask Radek if he can take over a little bit. I'm switching to you right now.
Yes, Lubov, thank you. Thank you for the introduction, and I will show you the practical part of this benchmark. So basically, I will introduce the case, and I will show you how the case is set up in TCAE. Okay, so if you go to our web pages for more information about this case study, and for more information in general, you can go to our web pages, and particularly in the case study section, you can find today's case, the FDA pump. So you can find it here. So if you click on it, so then you can read all the details about this benchmark, how the data looks like, how the simulation is set up, and all the details about the case in general. To read more about the results and about the benchmark, you can download this PDF. You can read all the details, and of course you can also download the case. If you scroll down to the bottom of this page, you can download this case, you can ask for trial, and you can do it by your own. So as all the information are available, so you can do it by your own. All right, so if I go to the benchmark case, so basically what you need is to have a nice geometry of this FDA pump. So in general, maybe I can go to our presentation, and what you need to have for all kind of turbomachinery applications is to have a nice watertight geometry, and particularly for rotating application, you need to do the splitting, which we called component thinking. So you need to split the domain into the rotating and stationary parts, and then these parts should be connected via the interfaces. So interfaces is standalone patches which connects the neighboring components. Then what you need also is to have the patches for each component, because then per each patch, which is defined by a standalone STL geometry, so you need to have as many STLs as you need for a good setup, for a good definition of the mesh boundaries, and later on for a good definition of the boundary condition for CFD simulation. So basically what you need is to have the splitting of the domain. It's a really detailed splitting, but at least what you need is to have the inlet and outlet from your domain or component. You need to have split the rotating and non-rotating walls, and possibly other geometrical constraints like some kind of periodic boundaries for the segment geometries or symmetries if the object is symmetry, but typically this is typical for external flow analysis. So the splitting is very important. So as an example, we can show how the rotor looks like here. So rotor is here is split into 4 parts. So here we have, if I double click the geometry, so I can open it in ParaView. So this is the part which is called rotor wall. So this is the non-rotating part of the geometry. Then we have the rotor part. Yeah, so this is the rotor part. I can color it with different color just to emphasize. So here we have the rotor. As you see, this part can be also used as a solid. So we have a special part of the solid geometry which can be used for FEA analysis. And then there are two inlet or two parts, two interfaces, inlet and outlet interface, which define the interface at the inlet from the inlet pipe, and outlet interface which is connected, I think, to the to the volute section. So all these STLs has to be created in advance. It can be exported in from your CAD geometry or designed directly in your CAD geometry, and then exported as STLs, and this STL geometry is then ready to be imported into the TCAE. Okay, so I will take directly the case. Here I have it. Here I download it and run it before our webinar. So I can directly open it. And let's have a look how the case is built. So this is the TCAE environment. It is implemented in ParaView as a plugin, so you can use all the functions, and there are many functions from ParaView. And above that, you can have this TCAE environment, so you can directly set your geometry, set your simulation setup, run it, and directly post-process the results. And you can use all the filters and and options which ParaView offers. So this is a standard layout. Here we have a render view where the geometry, input geometry, is already loaded. Each component is colored with different colors. So as you can see, here we have 3 components. When you run the simulation, so in default you can follow the residuals of your simulation runtime. So this is the resulting residuals for the first speed line. I will explain it later. And at the end of the simulation, you can also see this CFD or FEA reports when the simulation is finished, to see which sums up all the results or the integral values and all the quantities which are available from the simulation. So this you can see at the end. So let's go back to the beginning. So when you start setting up the case, so you always start with creating the computational domain. So for this purpose, here there is a TMesh module which is used for importing the geometry or external simulation, external mesh geometry, which is already designed for the simulation, for example, in MSH format, OpenFOAM format, or in general CGNS format. Whenever the TMesh module is set up, and then you can go for the CFD simulation. So here the TCFD module consists of several menus using which you preset the CFD simulation. And finally, if you want to go for FEA analysis, you can also use the FEA module and preset FEA simulation. The last two modules, TCAE is for the acoustics simulations, and the final TOPT is for the optimization loop or DOE design. So you just have explicit set of geometries, for example, and you are able to run it within a single click to reveal the CFD parameters of each of the design by one click. So let's start with the TMesh module. So let me click on the TMesh. and here you see all the menus using which you set the geometry. So the general section includes just the parameters which tells the software what will be the output of the mesh if it is designed, or you will create a CFD mesh or FEA mesh or both for example FSI application, or just for simple run all the analysis by one click. It means CFD and then FEA, and within FEA you can map the results from CFD or just use, for example, the rotation to get the displacement and other quantities without mapping the forces from the CFD simulation. Then, because the STLs doesn't include any information about the dimensions, about the units, so then you need to tell explicitly that the source geometry, the STLs, are already in meters or in any other unit. So this is important because sometimes typically you can get the STLs in millimeters, so you need to tell that the import STLs are in millimeters. All the modules include some kind of scripting environment where you can modify or tailor some kind of, or create a new function which will be included into the whole workflow. This can be done within each module. So if you need any special treatment of the STLs before meshing, before creating the computational mesh, you can add a script, and this is simply Python script, and there are some kind of function which can access parameters of TCAE in general. So this is kind of user-defined function can be defined here. Okay, but the main work should be done in a CFD mesh section. So here you define, in the rotation reference frame, you define the axis of rotation and axis of symmetry for stationary part. For example, in case of stators on axial machines where you do just a segment geometry, for example. But here basically you always need the static part and the rotating part, where the rotating part includes or defines the axis of rotation. Then in the components, here you define the components, as I mentioned at the beginning of my part, that typically you need to split the domain into the several components, where component define either static or rotational part. So here we have three components. So first component is the inlet piping, which consists of 3 STLs. So if you double click this part, so after importing the STLs, they will automatically appear in this table, and using these boxes you define the parameters of the mesh, and you define the type of the boundaries. But first of all, you can define a component name. Here you assign the static or rotating frame, which defines the physics. So if the component is treated as stationary or is treated as rotating, so then depending of the solver, like transient or steady state simulation and in transient with solid body motion, or just enabling the transient solver without solid body motion. So then you basically define the main properties here, if the component is rotating or not. If you double click every part, it is highlighted. So just to easily refer to this part, and to make it simple to assign the proper types and the boundary properties, boundary refinement, you can click on it and you see what you are setting up. So you set the type of the boundary. It means physical type, like the inlet or outlet, or inlet or outlet interface. So inlet is simply set as the inlet. Interface rotor is set as the outlet interface because the flow goes out at this part, and the rest, the wall is set as a standard wall. Reference frame is static for sure, and minimum and maximum refinement level sets the refinement of the background mesh cell size, so which is defined here. So this is the largest cell in the domain. So this is the initial state of the meshing. So you can imagine how cell, the sizing of each cell at the level 0, and this level means how many times the cells which are intersected by the given boundary will be refined up to the level, and the refinement means it is split into the new cell, let's say for the hexas you have eight new cells splitting for the cell at the level 0. So this is the background mesh wireframe. Now I've done many clicks here. So let's, maybe something is running on my background. Nevertheless, so this is set for the minimum and maximum level of refinement, and the last column is the layers. So for the rigid wall, you can add the layers, so inflation layers. So here we have an example of adding 3 inflation layers at the inlet extension wall. So then we can visualize the mesh to see how we set it. Okay, so this is the background mesh. We can get rid of this highlighting. So then there is an internal point, because based on the principle of SnappyX meshing, you need to set which part of the original background mesh will be kept for the simulation. So definitely we need to keep the inside part of this piping. So this point has to be placed somewhere inside our component geometry. And basically this is all what we need. And the same procedure is done for the other components. So again here, because this part is rotating, we need to set it as a reference frame as a rotating. Inlet and outlet interfaces now with respect to the given boundaries, and to connect it to the proper component. And here we have the blade, which is rotating, and rotor wall, which is non-rotating, because it is basically the casing of the volute. So in this way, we set again the minimum and maximum level of refinement and the boundary layers for the given parts. What I would like to mention here is, So it was about the boundary layer. So a few notes here. So here you just said how many layers will be built, and the particular parameters of the boundary layer is set here in the advanced meshing options. So now we are on component 2, and here is the layer, and here you basically define the parameters of the layer. So we have 3 layers with expansion ratio of 1.2, so it means sizing or expand ratio of the neighboring layers going from the wall. And here is the sizing of the layer. So here we set the final layer. So final layer will be the height of the final layer will be 25% of the original cell created at the given wall. So by using this relative sizing, you can adjust the parameters for the inflation layer. And last point I would like to mention here is when you setting the inlet outlet interfaces, so you need to create a connection, and the connection is done by right clicking on the given interface. So for example, interface rotor inlet is connected to the component 1, which is the inlet piping, to the interface rotor inlet extension. So if when you are starting from a scratch, you need to create a connection, and the connection is done by right clicking and clicking on the proper connecting interface. And just to check that your connection is done properly, you can go to the section to the section which is called component map. And here there's a nice graph which shows you the connection between each component. So if you made some kind of mistake, you will see some weird connection by the arrows, and just to connect, for example, component 1 to component 2 properly, you need to connect these two interfaces, as I already mentioned, by clicking on the interface and connecting it to the given neighbor. Right, whenever you are satisfied with the meshing, you can go to the first item here, to the manager, we call it, and to the team mesh run, and you can click here, mesh all by one click. And just to finish the team mesh part, I forgot to mention the meshing for FEA part. So if I go back to the team mesh and go to the bottom to the FEA mesh part, so this so the setting or the setting of the mesh for FEA analysis is much more simpler. You just need to import the geometry, typically a single solid STL, which defines the solid of the geometry which should be analyzed in the FEA. So you will import it, and just to see it, you can, so for example, the CFD mesh, I can click here, display, I can create some kind of opacity to see what is inside, and under the FEA geometry, you can see the imported solid. Yeah, so it basically copies the fluid domain of the rotor part. So this is the input geometry of the solid, and here the meshing engine is NetGen or GMSH. So NetGen is typically used, and here you just define the minimum and maximum sizing for the tetrahedrous elements and the coordinate. So some other detail, if you set the 0, so it some default value is used. So this is much simpler setup for creating the FEA mesh. So when your setup is done, you can click by mesh all, and all the parts will be meshed automatically, and any part can be visualized. So for example, what I can do, I can create new render view here and visualize, for example, the component 2, which is the mesh of the rotating part. And so we always strongly suggest to always check your resulting mesh visually, because this is the first check which tell you if your parameters and the geometry and everything follows the desired geometry, of course. So when I click here, CFD mesh, so now the CFD mesh should be loaded into the into the render view, and whenever the geometry is loaded, you can see the shape. So now I can zoom by this icon to see the topology. I can click here and choose the visualization surface with edges. So now we see the topology, and to see what is happening inside, we can click. So the CFD mesh, this item holds the geometry, and above it we can apply any filter. So for example, a slice. So I can slice it by this plane. So the plane perpendicular to the X direction. And whenever the slice is visualized, we can see the topology of the mesh intersected by this slice. So here again, I can switch surface with edges, for example, to see better shape of the cells, because ParaView uses some kind of triangulation, some VTK format to be able to visualize such a geometry. So we can get rid of this triangulate the slice, and then we see a more topologically more real view of the cell shape on this slice. So you can follow boundary layer, we set just 3 layers, which is here, and the refinement of the mesh. So because we set, as an example, if I go for the rotor parts, so for example on the rotor blade we set the level of refinement 0, the minimum and maximum 4. So as you can see on the flat parts, we can see the large cells, which is here, and on the rounded, more curved areas, we can see the level of refinement up to the 4, depending on the curvature of the geometry. Yeah, and this you can of course done for the other parts. So anytime, because the filter holds all the children data or ancestor data, so you can visualize also the component 1 directly, and directly, because now I am visualizing the slice, we can directly see the slice as well. So in this way, you should always check visually the mesh to see all the details, all the problematic parts, which is typical sharp edges, close gaps between two parts, etc. If these areas are meshed properly, and whenever you are fine with all these checks, then you can go for setting the CFD simulation. So basically the main part to have a mesh is a crucial part to have a nice and accurate CFD simulation and CFD simulation results, of course. So let's go for the CFD part. So in general, the simulation type, because we have several applications and we love the tailored solution to the given application. So we have several applications here, mainly connected to turbomachinery, but also for some kind of more general topics like the general stator or the type general or closed domain, etc. So here we have a pump. In the physics, here we preset type of the simulation, so time management. Here we are running it in steady state mode, but for more advanced and enhanced simulation, you can go for transient. Here the speed line means, because the benchmark was done for 2 different revolution, two different speed of rotations. So we set 2 speed lines, where one speed line holds a constant rotation speed. So we will have 2 speed lines, first speed line with 2 points and the second speed line with 4 points. And to be sure that the simulation is converged, we set 10,000 iteration for each point too. So this is the maximum iteration for converging the solver. And then I will show you how to set some kind of rules for stopping the simulation whenever the solution is converged. So next menu is the fluid properties. So here we define the fluid properties for the incompressible physical model. So as Luboš mentioned, this is for the ideal gas. Yeah, so this is the property of a water, as Luboš mentioned. Rotating reference frame here for the rotating section, so which refers to the rotating frame set in the TMesh module. So we have 2 speeds, because we have 2 speed lines, so we can set 2 rotation speeds. So first one is 2,500 RPMs, and the second one is 3,500 RPMs. So always check which units you are setting. This is typical misprint when you start the simulation from scratch. So always double check the units and the proper values. In the multiphysics, you can apply some additional physics or additional parameters to be simulated for the given type. So here we can have a calculated hemolysis index, which is kind of index which representing some kind of damage of the blood cells, etc. So for more information, you can refer, for example, to the PDF on our web pages. Turbulence model, here you can set the turbulence model. Typically, the default default value, default turbulence model is KMAG-SST, but you can go for another one if you prefer, depending on the application. Within the simulation section, here you set the solver parameters, like how many cores will be used for the simulation. So parallelization is available. There are no limitations, so you can use as many physical cores you have on your machine. There is no improvement if you use the virtual cores, so always use up to the maximum physical cores you have. Multi-threading is not here an advantage. Numerical order, first or second. Runtime evaluated quantities. This is important, so because we are looking for a steady state solution, but from the physical point of view, the physics behind, and mainly in the rotating machines, the physics is not steady state, so sometimes the steady state solver still some kind of oscillates around constant values. So therefore, for averaging this local oscillation, we can use this averaging window. So it depends on the magnitude of the oscillation and the periodic and the period. We can increase or decrease this averaging window to have a nice robust solution at the end. Maybe we will see this in the report, how it behaves, this averaging. You can ask for some advanced fields to be evaluated, like over shear stress, which is important for this blood like applications. We can also write these. So in default, all instant quantities are stored, but if you would like to also store the averaged quantities for further post-processing, for example, or just for the visualization, you can click it here, which fields to be, which field should be saved as a averaged fields. Efficiency probe. So for example, for pump efficiency is evaluated based on the torque. So you will choose the patches which will be used for evaluation torque, and as a pressure difference between inlet and outlet. So you can choose here what what patch will be treated as the inlet and what patch will be treated as the outlet patch. So it depends if you would like to include the pressure losses of the inlet of the piping, or you just need to evaluate the efficiency on the rotor section itself, on the rotor and volute, for example. So you can get for another interface. You can ask specifically for evaluating forces on a particular part of the geometry, as well as to follow any quantity within any point within the computational domain. Here, convergent check. So to be sure that, and basically for benchmarks, to be sure that the simulation is converged, we typically go for the wider of for the higher number of iterations and wider averaging window. And then you can say, okay, if because my target quantity is, for example, efficiency, the average efficiency, so we can tell, okay, if the average efficiency doesn't change more than this number in absolute values, it means 0.05%. So then you can stop the simulation before the maximum iterations are reached. So this is a stopping criterion. Here are some kind of parameters connected to the solver, like the relaxations, like the bounding limits for the given quantities, and some kind of solver setting some relative or absolute tolerances. The main, what you should take care of is the boundary conditions. So here we have 2 speed lines and 6 points altogether. So for each point, we define different boundary conditions. Here we define different volumetric flow rate in liters per minute, and this should be set for all speed lines and all points. Then also we add some quantities which is connected to the turbulence, and the same as the outlet. So because we are in the incompressible mode, we can set the reference static pressure at the outlet. So fixed pressure boundary at the outlet. For the walls, for each wall type, boundary for each component, we can set a wall boundary condition. So we have wall with friction, so-called no-slip wall boundary condition, and for the turbulent treatment at the walls, we use the low Reynolds flow function because we are in the range of y plus around 1, so we can go for low Reynolds. Otherwise, for not resolved boundary layer, we can go for the standard wall functions. Interface condition, so here we use standard AMI, so arbitrary mesh interface. But for example, for the segment and for periodic cases, we can go for the mixing plane for mixing plane averaging technique. And then finally, initial conditions. So we can set some kind of initial values for the solver to start with. Yeah, and finally, in the post-processing, here you just ask for some specific evaluations. Here you can set some kind of blade-to-blade evaluation and visualization. In the report section, you ask for the particular section within the report you would like to see at the end and your favorite units. And the last one are some kind of advanced features, how to save the data in which format for further post-processing in different softwares or for mapping to different kind of applications. All right, so this is a CFD, and as I said, again, if you are okay with the setup, you can click the run TCFD and wait for the result. And just to finish the setting part, we can also set the FEA analysis, where we set the finite element analysis as a fluid structure interaction. So you can ask to map the resulting forces from the CFD simulation onto the solid part, onto the FEA geometry. So basically, the forces from a CFD simulation is mapped on the solid, and using these new forces on the solid, you can perform the FEA analysis. Okay, let's go back to TFEA. So here we ask for fluid structure interaction. We take the mapping for TCFD results. We would like to also include the rotational forces, and the rotation speed is stating from the CFD simulation from the rotating frame. We would like to map forces. We use the relative pressure. So the relative pressure means is the original pressure which solver takes, which solver outputs. So it's not because the incompressible solver runs with the relative pressure, so-called kinematic pressure, which can be recomputed to the pressure in pascals, where the reference pressure is taken into account. But here we don't want to take into account the relative pressure, because the absolute pressure, because we just take care about the differences. The difference create the forces. And we would like to use the average quantities, because we have some kind of average pressure on the solid, so which creates the average force, and this average force will be mapped on the solid. We can also perform the model analysis, so to get the eigenvalues, eigenfrequencies for our conditions. So this will be also evaluated. With the solver, again, it can be parallelized. Here are some linear algebra solvers which can be used. Finite element order for higher displacement, higher deformation. We can enable the nonlinear equations. Again, the scripting can be done. Here you set the material properties of this. So this corresponds to some acrylic plastics, I guess. So this is the values of the solid or of the matter from which this rotor is made. Boundary conditions. So here typically the zero displacement is placed. So the zero displacement is placed on the shaft part. which can be chosen by the cylinder, or by the, for more general shapes, you can use the STLs to define the zero displacement regions on your solid. Here we don't need to solve the temperature, so we don't have any temperature region or external forces region. So we can also create an explicit force on a given part, but we don't need it here because the forces are taken from the CFD simulation. And again, you can adjust your report to your needs. So whenever you are ready, you can click Run All button, and all the parts like meshing procedure is run. After the meshing is done, the CFD simulation is run, and whenever CFD simulation is finished, then the TFEA simulation is run. Everything you can follow runtime as I presented here. You can also see all the quantities during the simulation. You can choose, for example, to follow the efficiency or head or everything, every other quantities. And at the end of the simulation, you will see the report, which can be also opened directly from the case. Yeah, you can see it. You can see it in the GUI, or later on, you can directly find it within the project. So if you go to the TCFD part, here you have the report, and you can open this report in your HTML browser. Here you have some statistics about each speed line. Here are the final outcome of the whole simulation. So the efficiency, flow rate versus efficiency graphs for each speed line, and the same graph, but now for the total pressure difference. For all the points and all the simulation, you can see the details, how what kind of mesh was generated, all the parameters of the mesh. You can also follow the Y plus on the walls as an averaged value, or particular for each part of the wall. And again, you can see, for example, the head values, the resulting values for speed line, first speed line, and the instant values throughout the simulation. So this is the instant head. So you can see the local oscillations and the average solution, which is depicted in the red line. And for example, here, because the red line was nicely and constant within our convergent check limits. So here you can see the straight line typically shows you that the rest of the iteration was skipped because the convergence criterion was satisfied, and the same for the efficiency and all the other fields. And the same you can see for the FEA part. So for example, now I will show you in the GUI directly. So you can switch here, you can switch here for the TFEA run, TFEA HTML report. It looks very similar. So again, you have here some statistics about the simulation, about the setup, and then you see the results. So some static analysis, so some kind of maximal, minimum displacement and stresses. Here you can also see kind of visualizations, just to see the first view on the, for example, von Mises stresses or the displacements. And this is done also for the model analysis. So again, first 3 eigenfrequencies and the displacement for each eigenfrequency. Of course, the results can be visualized directly from GUI. So if I open new render view and I would like to see the results of the CFD simulation, so I can go for the CFD run, TCFD run, and here display the new one. So now all the results are loaded into the GUI, and then you can visualize all the fields on the resulting mesh. So let's wait for a while, because all the mesh with all the results are loading now into the GUI. And okay, and we have here the stationary results. So when I click on the eye, to visualize it in the render view. So now we will be able to see the simulation domain. Okay, now it's loading. Yeah, we have several millions of cells here. So I hope the mesh will be loaded soon. And then of course you can play with it. Yeah, now so this is our domain. Now it's visualized with the static pressure distribution, but you can go for any other field like velocity magnitude. Just to see the inside, you can apply a slice where I have it, the slice. Okay, so I need to click on here on the stationary, and somewhere I can apply it. Okay, where is my, okay, I need to click apply, I guess. Yes. And then you can apply any slice, you can change the field and do some kind of visual analysis, create a fancy render views with streamlines, with glyphs, and anything you want to visualize. Okay, so maybe we are almost at the end, so I will switch the presentation back to Luboš, and maybe meanwhile I will prepare some kind of visualization. So thank you for thank you for watching until now, and now back to Luboš.
Absolutely, yes, Radek, thank you again for your part. It was again very informational and practical. Thank you. And okay, we will move in the presentation to, yep, there was the expert on air, and now we are moving to Q&A, and slowly we will move to conclusion of the webinar. So we have a couple of questions here. It's difficult to pick a representative one, but still we have a few. So David is asking, what would be the difference if you used the blood instead of water? Yeah. So I think I could answer this one. Well. So first of all, this case study is available on our website. So if I'll go to our website, cfdsupport.com, in case studies, there's this rounded, really rounded shape with kind of strange blades impeller, and if you enter this website, there's all the information where you can observe and you can learn all the details, and also the case is downloadable, and it can be run and tested, and you can find also a couple of references and the hard data if you want to. So that's information number one. Yeah. The case study is based on mainly on this article from Mr. Malinauskas, if I say it correctly. And so the case is available. And back to the question, so difference between blood and water. So after a lot of speculations here, we decided to simulate with water, because then you're sure that you're not bringing another level of possible mistakes to the case. I can tell that during my PhD studies, I've been involved in a couple of hemodynamics projects, which dealt with the hemodynamics deals with blood flows, and blood is very specific fluid, and it's important what type of the blood features are you going after, what are you going to follow. If you follow, for example, the rheology based on shear thinning property, that means the increase in shear rate, the velocity gradient, the velocity decreases, and this effect, for example, can be simulated if you change this Newtonian fluid to non-Newtonian fluid and pick appropriate model for blood, and this effect, this shear thinning effect, has specifically large effects on very thin veins and in very thin tubes, while in larger tubes, as for example is a few millimeters in diameter, for example, and this, which is certainly our pump here, then the effect of shear thinning, it almost disappears, and then the blood behaves like a normal fluid, like water, for example. Its non-Newtonian property disappears a little bit, because it disappears in fact because in the where there's a lot of space, there's lower these strain rates, velocity gradients, and then the flow, the blood behaves then like almost like a water. On the other hand, if the tube would, if the vein in human body, or in the for example in this mechanics, would be, for example, 1 millimeter and less, then the shear thinning property of the blood becomes all of a sudden very important. So in this kind of simulation, it's not that important, because still the impeller diameter is something like 50 millimeters. So it's relatively large, and blood works the same way as water. If I make this really, I would keep it in the simple, on the simple level. Okay, we have another question about relatively high RPM. It's again a very common question. So high RPM, which is typical for small machines, right? The machine, in terms of centrifugal pumps, this pump is still very small, right? And what is small? It has to have a large, very high RPMs, right? So about 3,000 and 3,500 RPM is typical number for such a size of centrifugal fan, which delivers certain flow rate, right? So it depends on the size of the machines. For example, in the project we are dealing at the moment here at CFD Support, the axial pump it has only 1 centimeter in diameter, so it's really small tube. It's axial fan. It's axial pump, and it has 8,000 RPM, so it's even much more faster. So yeah, for blood, high RPM is very typical for the pumps, and yes, high flow rates again produces quite some velocity gradients, and that could lead to to hemolysis, which is the corruption, the damage of the red blood cells, and it's another issue. We do not want to chop the red blood cells, because they're quite large, so we do not want to chop them into a mesh which would not carry any oxygen anymore. Okay, so that's the high RPM. Yeah, very typical for blood flows, because sometimes you can put the pump inside the human body. Then definitely the pump has to be small and also energetically efficient, not to stop everything flowing when the batteries discharge, for example. But that's another topic. A question on Radek. Can you comment on turbulence modeling in the case?
Yeah, but we can do it very quickly. Yes. So I don't know if you can.
Maybe you can just say it. Just say it, Radek.
Okay. Yeah. So the turbulence model is set within the physics section, and there is a K omega SST turbulence model, and the proper choice always depend on the application, on the experience with the model. So K omega SST is choice number 1 typically, or another option is to use any K omega family turbulence model, like K omega or realizable K K epsilon, sorry, K epsilon models. There is also a Spallard Almaraz, which is not so suitable for the turbomachinery application. It's for external aerodynamics applications. And the last note on the transient simulation, there can be a DES-like models can be also applied, which is a hybrid method between the LES and standard. Yeah.
But anyway, thank you for this. Definitely, if we don't have any special requirements, then the K omega SST is the safest choice for steady state simulations for sure. Yes, and I think it's maybe it's a little bit time. The information is available on the website anyway, so anyone can go there. And if you have any more questions, feel free to come back, and we'll be happy to answer your questions and do our best to make everyone happy if it's possible. Okay, this could be it. So the end is always quick. So yep, thank you for coming. Thank you for watching us. And if you have any questions, feel free to come back to us, and we will help. And I guess this would be it for today. So bye bye.
Yeah, bye
Everyone.
See you next year.
Yes, and Merry Christmas.